reviewing. So if you've been absent and have missed any notes, there should only be 4 sections. But if you've missed any, make sure you get those caught up by tomorrow. All right, so today we're going to talk about exponential functions. So for the most part this year, we have just talked about linear equations, linear functions, linear expressions. So the first thing that I kind of wanted to throw out there is the difference between what we would call an exponential function and exponential equation, all of that thing, as opposed to linear. So we started this year, and we probably talked about like a linear expression, so x plus 3. And then we moved on to a linear equation, so 5 equals x plus 3. And then we moved even further to a linear function, y equals x plus 3. So x plus 3, just plug in the number, kind of right, evaluates for you. This one you can solve, get an answer. This is a function you can graph it. Now what we're going to move on to today is we're going to talk about exponential functions. Okay? So an exponential function is going to be in the form y equals a times b to the x power. So the big thing you're going to see whenever you have an exponential function, the x is the exponent. The x is the exponent. So notice it's b to the x power. Okay? So if you're looking at the function, if you're actually looking at the equation, that they're pretty easy to pick out because the x is going to be the exponent. Now, they can look a little different. So we could have something that says f of x. If you remember, that's function notation from chapter 4. We just talked about it just briefly. But it could look like 2 times 3 to the x power. It could say y equals negative 4 to the x power, or g of x equals 0.3 to the x power. Notice on all of these, the equations look different, but they all have the x as the exponent. Now, if you look at the graph of an exponential function, the graph of a linear function is pretty simple. The graph of a linear function is linear is a, what does the graph of a linear function look like? When we graph slope and y-intercept, what do we create? A line, thank you, a line. So a linear function creates a line. An exponential function creates a curve that's going to look like one of these 4 options. Now, depending on what your function looks like, depends on what your graph is going to look like, but the general idea is going to be the same. So there's going to be kind of 2 parts to the graph. So there's 2 graphs here. There's 2 graphs here. One's red, one's blue, one's red, one's blue. So 4 different functions here. So if I look at this red one, what happens here is it kind of starts off increasing slowly, and then it like jumps and increases really, really fast. Or the blue one starts decreasing pretty slowly, and then it like just drops off really fast. Okay? Or it could just do the opposite, where, it decreases really fast, and then it kind of levels off. It's still decreasing, but just not very fast. Or it could increase really fast and then kind of level off. But you're going to have these 2 areas. One where there's slow growth, where not much is changing. It's increasing a little bit or decreasing a little bit, but not much. And then it's going to either take off one way or the other, or it'll just do the opposite. Now, one of the things we're going to be doing today is looking at a table of values to decide if it's going to be an exponential function or not. Now, if it's a linear function, and you were looking at the table of a linear function, here's what you would see pattern-wise. It might say like 3, 5, 7, 9. If you're looking at a linear function, the y values are going to have a constant rate of change. Meaning, to get from 3 to 5, you're going to add 2. From 5 to 7, you are going to add 2. From 7 to 9, you are going to add 2. And this pattern would go on and on and on. Because think about it. If it's a line, every time you move along the x-axis, right? -1, 0, 1, 2. If you're just going up 2, right? would be a straight line. It's a constant increase. Okay? What happens with an exponential function, if you look at this pattern here, to get from -1 to -3, and then -3 to -9, and then -9 to -27, what's that pattern? How would you get from -1 to -3 and -3 to -9? Times what? Times 3, right? You would multiply by 3 each time. This is called a constant ratio. A constant ratio, meaning you're going to multiply or could be divide. Okay? But if it's linear, it's going to be a constant rate of change, meaning you're adding or subtracting each time. If it is exponential, you're going to be multiplying or dividing. Okay? Now, one of the other things you're going to be doing today is graphing exponential functions. So we're going to go through and practice this one, graph this exponential function here. So we are going to graph y equals 2 to the x power. So to graph a function, I know with linear equations we learned how to find the slope and the y-intercept and graph it using that way. But for most functions, other than linear functions, really what you have to do is just have to come up with a bunch of values. Because remember, the graph of the function is a picture of all of the solutions. Okay, so I need to find a bunch of solutions. So what we're going to do here is we have our x column, -2, -1, 0, 1, 2. Give you those ones. Okay. We're going to plug these numbers in for x. Now notice the x is the exponent here. So when you plug in -2, you're going to take 2 to the -2nd power. Now remember, I can't take 2 to the -2nd power because it's a negative exponent. If it has a negative exponent, remember what we do with that? Flip it to the denominator, and it's going to be 1 over 2 squared, which would be 1 over 4. Then we're going to plug in -1 for the x, which means I'm going to take 2 to the -1st power. Remember, I can't take 2 to the -1st power because it's a negative exponent. So we're going to flip that 2 to the denominator. The -1 becomes a +1, so it's just going to be 1/2. When I plug in 0 in for x, we're going to take 2 to the 0 power, and anything to the 0 power is 1. And then we're going to plug in 1 for the x, so we'd have 2 to the 1st power, which is just 2, and then we're going to plug in 2, and I'd have 2 squared, which is 4. Now what I've done here is I've created 5 solutions. When you plug in -2, you get 1/4. -2, 1/4, that's a solution. I could plot that. -2, 1/4, it's just going to be just barely above the x-axis right there. -2, left 2, and up a fourth a unit, right? Just barely. -1, 1/2, so left 1 and up a half a coordinate. That's also a solution. 0, 1, so you're going to stay right there in the middle, but go up 1, put a point. 1, 2, so right 1, up 2, and then 2, 4. Now, keep in mind, like we've always talked about when we're graphing, these are only 5 of the infinite number of solutions for this function. I can plug in -3 for x. I can plug in 3 for x. I can plug in 10 for x. I can plug in whatever I want for x. These are just 5 of the possible solutions. So to show the entire function, what you need to do is connect the points with a smooth curve. So we connect them. And notice there's a period of slow growth and then a period of rapid growth. This is what all of your functions should look like today. Okay, questions on that? Okay, let's get this glued into should be page 9, 7.6 exponential functions. Function, we're going to evaluate exponential functions and graph exponential functions. So, first one, I'm going to give you a table, okay? So we're going to do a row for the x's and a row for the y's. Okay, going to look like this. Now the x coordinates are just going to be 1, 2, 3, 4. The y coordinates are going to be negative 1, 1, 3, and 5. Okay, so what we're going to do here is we need to decide if it is an exponential function or if it's a linear function. So what you're looking at is you're looking at the pattern of y values. Because notice the x values are just 1, 2, 3, 4. They're not really, I just up in by 1. But if I look at the y values, if I go from negative 1 to 1, from 1 to 3, from 3 to 5, what's that pattern there? You're adding 2. Anytime you're adding or subtracting, think about it. If you went from 1, 2, 3, 4 on the x, you're just going over by 1, and then you're plus 2, plus 2, plus 2, plus 2. That'd be a straight line, right? You're just adding 2 each time. So this is going to be a linear function, and because you're adding 2 each time, that could be a good explanation there. Okay, let's do another table. So x row and a y row. We'll do 1, 2, 3, 4 again for the x's. And for the y's, let's do 3, 9, 27, and 81. Now remember to decide whether it's linear or exponential. Notice the x's, same thing, it's just 1, 2, 3, 4. On the x's, you're just going over 1. But if you look at the y's, we're going from 3 to 9 to 27 to 81. What's this pattern here? You're multiplying by 3, right? Since you are multiplying, this is going to be exponential because you are multiplying. So for the table, you're looking at the pattern of y values. Now, if you have a function rule, these ones are a little easier to see. Y equals 5 times 2 to the x. Now, looking at a rule to determine whether it's exponential or linear, you need to find the x. In this case, where's the x? Or what is the x? It is the exponent. So guess what? If it is the exponent, it is an exponential function because the x is the exponent. Okay, number 4, we have y equals 3x minus 6. So once again, to decide what type of function it is, you need to find your x. Now in this case, it's 3x minus 6. And if we look at this, this looks like something that we would have graphed back in chapter 5 because I have a slope, I have a y-intercept. If you have a slope and a y-intercept and the x is just 3x, right? This is going to be linear. If I were to graph this using the slope and y-intercept, it would be a straight line. The slope of 3 and a y-intercept of negative 6. So we could say it's linear because it is in the form y equals mx plus b. Okay, now moving on to actually using exponential functions, let's talk about how we evaluate exponential functions. Okay, so number 5, let's say I have the function f of x equals, remember the f of x, I haven't given you the actual function yet, but f is the name of the function. It's going to be function f. The variable in the parentheses, that's going to be your input. So I know I'm going to be plugging in x's, okay? And function is going to be 7 to the x power. So think about your function machine. What you're plugging into your function is going to be x's. And the rule, you're going to take 7 to the x power. So what we want to evaluate this for is we want to evaluate this for x equals 3. So what this means is I've got my function machine. I'm going to drop a 3 into my function machine. Now what that looks like in function notation, we would call that f of 3. We want to find the value of f when I plug 3 into my function. Well, when I plug 3 into my function, it means I'm going to plug a 3 right there in for x. So it's going to be 7 to the third power, and 7 to the third power would give me 343. So just plugging that in for x. Okay, number 6, what if we have g of x equals, so notice this one, this is function g, but I'm still plugging in x values, and here's my rule. Negative 2 times 3 to the x power for x equals negative 3. So kind of like the last one, this negative 3 is what you're going to plug into your function, which means you're going to plug that in for x. So we are trying to find g of negative 3. So the first step, we're just going to take negative 2 times 3 to the, instead of x, we're going to plug in negative 3. Now, think back to everything that we've talked about this chapter. You cannot evaluate 3 to the negative third because it has a negative exponent. The 3 needs to move. Now remember, the negative 2 is fine because it's not an exponent. It's just a negative 2. The negative 2 is going to stay in the numerator. The 3 is going to get kicked to the denominator, and the exponent becomes a positive. And then we could do negative 2 over 3 cubed, or 3 times 3 times 3 is 27. And we'll just go ahead and leave it as that fraction, negative 2 over 27, because we can't reduce that. Okay, let's try number 7. Okay, this time y equals 0.3 times 0.2 to the x power. Nice little decimals there. And we want to evaluate for x equals 4. So just like the last one, just not in function notation, you're going to plug a 4 in for x. So we're going to take 0.3 times 0.2 to the, and we're going to plug in 4 for x. Now always remember, order of operations is always a thing. You have to do exponents first. You'd have to take 0.2 to the fourth power first. 0.2 times 0.2 times 0.2 times 0.2, which would give you 0.0016. Then you can multiply by 0.3, which, this is a lovely little decimal, gives you 0.00048. And we need your calculators today for sure. Okay, last one of these, number 9. Okay, this time, my function is going to be h of q. H of q. Now, before I even give you the function rule or what we're plugging in, notice the function in here is h. And this time, I'm plugging in cubes. Not x's, I'm plugging in cubes. And my function rule here is negative 0.2 times 3 to the cube. Notice this time in my function rule, there's not an x, it's a q, because that's what my function rule tells me. And we are going to evaluate for q equals 5. Now, although it's different letters, different variables, notice it gives me a value for q. There's a q in my function, so we're still plugging that number into your function rule. So we're going to find h of 5. That's what it tells me to evaluate for. negative 0.2 times 3 to the 5th power. Like the last one, make sure you do exponents first. So you do 3 to the 5th power first. 3 times 3 times 3 times 3 times 3 should give me 243. And you're going to multiply that by negative 0.2. And it gives you negative 48.6. Okay, last thing you're going to do. You're only going to have to do 2 of these. Let's graph another function. So I want to graph y equals negative 3 to the x power. Now when you get to your homework, it's just going to give you the function. It's not going to write a table for you like I did on the left-hand side, but I want you to set up your table when you get to your homework the exact same way we're going to set this one up. So you're going to go ahead and create your table. So you need a column for your x's. Maybe leave a column to do some work. It's going to spit out your y values. And I want you to plug in 5 values. I want you to find 5 solutions. So you are going to plug in the same x values when you guys get to your homework. Okay? I want you to plug in negative 2, negative 1, 0, 1, and 2. So you have 2 of these on your homework. I want you to set up your table the same way. The only thing that's going to be different is it's going to be a different function. So we're going to do exactly what we just did on the left-hand side. These are the numbers, these x values are the numbers you're going to plug in for x. So we're first going to take negative 3 to the negative 2nd power. Now be really, really, really careful here, because remember I can evaluate the negative exponent, but also remember that the exponent only applies to the number right underneath it. So in this case, the negative is not included. The negative is going to stay with the 1 in the numerator. You are going to move the 3 to the denominator, and the negative 2 becomes a positive 2. So 3 squared gives me 9, so this is going to be a negative 1/9. We're going to do the same thing with the negative 1. Negative 3 to the negative 1st power. But same thing, the only thing that's being raised to the negative 1st power is the 3. The negative is going to stay in the numerator with the 1, so you get negative 1/3. When you plug in 0, it'd be negative 3 to the 0 power, but once again, the only thing being raised to the 0 power is the 3. That negative is still there, so you should get negative 1. And then I do negative 3 to the 1st power, which is just going to give you negative 3. And then when you do negative 3 to the 2nd power, same thing as all the other ones. The only thing you're squaring is the 3. You're not squaring the negative. So negative 3 squared would give me negative 9. Okay, now, one kiss.
So, negative 3 to 0. Why do you still have to, like,
I was just kind of showing you that you're only taking the 3 to the 0 power, not the negative. That's why I circled it. So, yeah. I probably shouldn't have circled that. That's probably confusing. So, yeah, I was just showing that, yeah, this is the only thing being raised to the 0 power. Yeah. Okay, so now, whenever you're ready to graph, we're going to go ahead and draw a coordinate grid. On the x-axis, we need negative 2 to positive 2. Notice on the y-axis, I need to go all the way down to negative 9. So try to make it as even as possible. It doesn't have to be perfect. The more even you make it, the better your graph will look. And then we're going to go ahead and plot our points. So negative 2, comma negative 1/9. So you're going to go left 2. When you go down 1/9, that's just barely underneath that x-axis. Down a 9, I mean, that's just like right underneath 0. And negative 1, comma negative 1/3 really should be just a little bit underneath that one. 0, negative 1, just going going to go down 1. 1 comma negative 3, and then 2 comma negative 9. And then once you plot your points, connect them in a smooth curve. And notice we have a period of slow decline, and then it kind of drops off there.